October 31st, 2025, Halloween morning. While most of the northern hemisphere wakes to costumes and candy, a postdoctoral fellow named Chiching Zhang sits at the Lowell Discovery Telescope in Arizona, fingers on controls, eyes locked on coordinates. 16 degrees from the sun, low eastern horizon, morning twilight. He is hunting something that has not been seen optically from Earth's surface in over a month. An interstellar visitor, a comet that passed closer to our star than Mars orbits. A body that brightened faster than any comet ever documented, turned bluer than the sun itself, and disappeared behind solar glare at the exact moment scientists most wanted to watch it. Now it emerges. Zhang captures it. A white dot, slightly fuzzy, moving against static stars. The first confirmed optical ground-based image of 3I Atlas after perihelion. The first glimpse since it completed its closest solar approach on October 29th, just 2 days earlier, at 203 million kilometers. This is not just another comet photo. This is the baseline, the reference frame. The moment we learn whether the rapid brightening, the impossible blue color, the unprecedented behavior near the sun, whether any of it survives the encounter, and whether the debris cloud predicted by the physics must be there, or whether something else entirely is happening. 3I Atlas, the third confirmed interstellar object in human history, discovered July 1st, 2025 by the Atlas Survey Telescope at Rio Hurtado, Chile, moving at 61 kilometers per second relative to the sun when spotted. Hyperbolic trajectory, eccentricity approximately 1.000016, not bound to our solar system, a wanderer from another star, possibly 7 billion years old, older than our entire planetary system by 3 billion years, following a retrograde orbit aligned within 5 degrees of the ecliptic plane, a configuration with a statistical likelihood of 0.2% for random interstellar arrivals. Already active at discovery, already releasing gas and dust at 4.4 astronomical units out, already showing the fuzzy coma that marks a comet awakening. But by mid-September, ground telescopes lost it. Solar elongation dropped below 30 degrees. The comet crossed into conjunction with Earth on October 21st, placing it directly behind the sun from our perspective. 8 days before perihelion, 8 days before the closest approach when comets typically surge in activity, when ice sublimates in massive quantities, when the physics of solar heating reaches maximum intensity. We could not watch. Space-based coronagraphs could, Stereo A's Secchi instruments, Soho's LASCO C3, GOES 19's CCOR1 coronagraph. They tracked 3I Atlas through September and October as it plunged toward perihelion. And what they recorded stunned the observers. Zhang and Carl Badams from the U.S. Naval Research Laboratory analyzed the coronagraph data. They published their findings. October 28th on the Archive preprint server, paper number 25, 10.25035, the brightness scaling, heliocentric distance to the power of negative 7.5 plus or minus 1. That is not normal. Most Oort cloud comets brighten at rates between negative 2 and negative 4. 3. I Atlas brightened nearly twice as fast as the most active known comets. The CCOR1 instrument resolved an extended coma approximately 4 arc minutes in diameter, roughly 300,000 kilometers across. LASCO color photometry showed the comet distinctly bluer than the sun, not red, as dust-reflecting comets appear, blue. Consistent with massive gas emission, carbon molecules fluorescing, dicarbon and possibly ammonium radicals contributing visible light. The cooling effect of carbon dioxide sublimation may have suppressed water ice vaporization early in approach, creating a reservoir that released explosively near perihelion. Perihelion occurred October 29th at 1.36 astronomical units from the sun, approximately 1147 universal time, 203 million kilometers, just inside Mars orbit. Magnitude extrapolated to approximately 9 based on coronagraph photometry, significantly brighter than the predicted magnitude, 11.5, but from Earth, invisible, hidden in solar glare. The geometry prevented observation precisely when the comet underwent its most dramatic transformation. Now, Zhang captures the first post-perihelion ground image. October 31st, the Lowell Discovery Telescope, a 4.3-meter instrument at Flagstaff, Arizona, one of the few large telescopes capable of pointing low enough on the horizon to acquire 3I Atlas this soon after perihelion. Zhang positions his telescope when the comet sits roughly 16 degrees from the sun, just clearing the eastern horizon during morning twilight. He exposes. He stacks frames. the comet appears, a bright white dot, slightly fuzzy from the coma. A star above it shows motion distortion. Zhang posts the image with coordinates, the first optical recovery, the baseline measurement. Scientists worldwide need this. They need to know the coma diameter, the tail structure, the brightness, the color. They need to compare pre-perihelion observations with post-perihelion reality to understand what happened during conjunction. If you value documented astronomical history like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. This script is researched and factual, using sources from the Arxiv preprint server. Specifically, paper 25 10.25035 by Zhang and Badams, published October 28th, 2025 DARS, and Live Science Reporting. By Patrick Pester, published November 3rd, 2025, documenting Zhang's post-perihelion observations. These are peer-reviewed or journalistically verified sources tracking real-time scientific observations of an unprecedented interstellar event. Now back to the information. Zhang does not stop with the large telescope. November 2nd, Sunday morning. He takes a 6-inch Ritchie-Chrétien reflector, a 152mm amateur instrument, to test visibility. Clear sky, low eastern horizon. He finds it 3 iAtlas shows as a smudge, faint but detectable. He posts this to his commentary blog. The significance. Standard amateur telescopes across the northern hemisphere can now observe this interstellar visitor, not just professionals, citizen astronomers, networks like Unistellar's 25,000 global observers, the SETI Institute. Anyone with a decent telescope and clear skies, this democratizes the observation window. It means hundreds of independent data points. It means distributed monitoring as the comet recedes from the sun, tracking changes in brightness, tail morphology, coma expansion. Zhang tells Live Science the comet will not look impressive, just a smudge, but an increasingly visible smudge. He predicts within 1 week the comet will reach 25 to 30 degrees solar elongation, allowing major observatories worldwide to begin systematic follow-up. The November 1 to 3 window matters because it establishes the immediate post-perihelion state. Was there fragmentation? Was there an outburst? Did the nucleus split? Did massive debris clouds form? The physics of 3 iAtlas near perihelion demands answers. Avi Loeb, professor of astrophysics at Harvard University and chair of the Galileo Project, calculated that if 3 iAtlas exhibited non-gravitational acceleration near perihelion, a deviation of 4 arcseconds in right ascension reported by ALMA radio observations, it must have lost at least 15% of its total mass. For a nucleus estimated between 0.44 kilometers and 5.6 kilometers in diameter, that means over 5 billion tons of gas and dust ejected. A massive debris cloud, observable, unmissable. If the ground images from November 1 to 3 show no such cloud, if the coma appears normal, if the tail structure remains consistent with pre-perihelion observations, then something does not fit. Either the ALMA positional data reflects measurement uncertainty rather than real acceleration, or the acceleration mechanism differs from standard cometary outgassing. Loeb suggests this as a potential 10th anomaly for 3 iAtlas, adding to the 9 already documented. November 3. iAtlas passes 0.65 astronomical units from Venus. 97 million kilometers, too distant for Venus orbiters to capture useful images, but close enough that the geometry shifts. The comet moves northward from our perspective, climbing higher above the eastern horizon each morning. Visibility improves daily. By November 9th, the comet achieves 10 degrees altitude just before dawn for observers at 40 degrees north latitude. By November 16th, altitude doubles to 20 degrees. The moon phases out of interference. From November 16th through approximately December 2nd, dark skies. Optimal imaging conditions. The comet transits from Virgo into Leo in early December, passing 1.8 degrees south of Regulus, the bright alpha star of Leo, on December 27th. This close approach to a first magnitude star provides a natural reference point for amateur observers and a calibration target for photometric measurements, but the critical window is now November 1 to 3, the first ground-based optical data immediately following perihelion. Zhang's images show a condensed nucleus region, no visible fragmentation. The coma appears intact. Preliminary reports suggest the comet may still be brightening post-perihelion, but more data is needed. If brightening continues, it supports ongoing volatile release, potentially from water ice that was suppressed pre-perihelion by carbon dioxide cooling. If brightness plateaus or declines, it suggests perihelion-marked peak activity. The color data from these early November observations will be crucial. Pre-perihelion, the comet showed reddening colors through July, consistent with increasing dust production. By late August, Gemini South telescope images revealed the anti-solar dust tail had grown to 30 arcseconds, approximately 56,000 kilometers. Then the blue color near perihelion. If November ground observations confirm a return to red, it indicates the gas-dominated phase was transient, tied specifically to perihelion heating. If blue persists, the gas emission continues at high rates. The timeline tightens. November 4. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, passes within 64 million kilometers of 3I Atlas. The spacecraft, en route to Jupiter's icy moons Ganymede, Callisto, and Europa, activates its Janus Visible Imager, MAGIS infrared spectrometer, an SWI submillimeter wave instrument. The observations will not return to Earth until February 2026 due to JUICE's current data transmission rate. It uses its medium-gain antenna, while the high-gain antenna serves as a heat shield near the Sun. But when the data arrives, it will provide the first space-based spectroscopy and imaging of 3I Atlas in its post-perihelion active state. JUICE observes from a different vantage point than Earth, offering stereogeometry to constrain coma structure and tail orientation. The scientific community mobilizes. The International Asteroid Warning Network, IAWN, announces a campaign from November 27th, 2025 through January 27th, 2026, targeting 3I Atlas for astrometric observations. The goal: improve methods for measuring comet positions, despite the extended morphology of comae and tails that can systematically displace centroid measurements. The Minor Planet Center, which coordinates such campaigns, emphasizes that comets present unique challenges. Their fuzzy, asymmetric structure makes precise astrometry difficult, but precise astrometry is essential for refining orbital elements, for predicting future positions, for detecting any non-gravitational perturbations. The campaign will hold a workshop on techniques for accurate comet measurements, then apply those techniques to 3I Atlas observations over 2 months. This is not just academic. If 3I Atlas shows unexpected trajectory changes, if the orbit deviates from gravitational prediction, the astrometric data will quantify it. The ground images from November 1 to 3 serve as the foundation. They establish the reference epoch, Zhang's October 31st observation at Lowell, exact position, exact time, exact magnitude. His November 2nd observation with amateur equipment, confirmation that smaller telescopes detect the comet, expanding the observer base. By November 3rd, reports emerge from multiple amateur astronomers across the Northern Hemisphere. Italy, Germany, United States, clear skies, low horizons, smudges in the field, coordinates match. 3I Atlas is confirmed visible to distributed observers. The data begins accumulating. Each observer submits positions to the Minor Planet Center. Each observation refines the orbital solution. Each image captures a snapshot of coma and tail evolution. The collective effort builds a time series record of the comet's post-perihelion behavior. This is documented history, not speculation. Zhang's observations appear in the scientific record. The Archive preprint server hosts the rapid brightening paper. Live Science, Universe Magazine, Dagens, Dim Sum Daily, and multiple other outlets report the observations in real time. The Lowell Observatory confirms Zhang's use of the Discovery Telescope. The images circulate through the astronomical community. Professional researchers analyze them, amateur astronomers replicate them. The data is open, the methods are transparent. This is how science works. Real observations, real instruments, real dates and times, verifiable. If you value documented scientific discovery like this, subscribe. It is the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources including the Astronomy and Astrophysics Journal article by Santana Rose and colleagues on temporal evolution of 3I Atlas, published September 26, 2025, and the Archive preprint by Maggiolo and colleagues on galactic cosmic ray processing, published October 30th, 2025. These sources provide peer-reviewed analysis of the comet's physical properties and evolutionary history. Now back to the information. The November observations matter because 3I Atlas is not just another comet. It carries information, physical information, chemical information, historical information, the nucleus, estimated now at 0.32 to 5.6 kilometers diameter based on Hubble observations through August, formed in another planetary system. It condensed from a protoplanetary disk around another star. It incorporated volatiles, water, carbon dioxide, carbon monoxide, reflecting the chemical composition of that disk. It ejected from its home system, possibly through gravitational interactions with giant planets or close stellar encounters. It drifted through interstellar space for billions of years, bombarded by galactic cosmic rays. Those high-energy particles penetrated the surface, converting carbon monoxide to carbon dioxide, synthesizing organic crusts, processing the outer layers into irradiated material. Laboratory experiments demonstrate these processes. When 3I Atlas outgasses, it samples that irradiated zone, approximately 15 to 20 meters deep based on erosion rate estimates. It reveals not the pristine interior, but the processed shell shaped by billions of years in the void. This fundamentally changes interpretation. Early hopes that interstellar comets would reveal unaltered material from distant star-forming regions face a challenge. Long-residence interstellar objects like 3I Atlas primarily expose cosmic ray-processed material, not primordial compositions, the rich carbon dioxide content. The unusual nickel vapor detections by the Very Large Telescope, the extreme negative polarization reaching a minus 2.7% at 7-degree phase angle, unprecedented among all known comets, these may all trace to the radiation crust. The November ground observations capture the tail end of this story. As the comet recedes from perihelion, as outgassing rates decline, as the coma thins, we see the transition from peak activity back to quiescence. If the comet underwent major mass loss at perihelion, the coma should remain expanded. Dust production should stay elevated, the tail should persist. If the activity was a transient burst, the comet should dim rapidly, the coma should contract, the tail should fade. Zhang's images and the subsequent amateur network observations over November and December will distinguish these scenarios. The brightness curve provides the diagnostic. Zhang and Badams reported the rapid brightening scaling as heliocentric distance to the negative 7.5 power through perihelion. That is steep. Extrapolating forward, if the same power law holds in reverse, the comet should dim quickly as it recedes. But comets often show asymmetric brightness curves. Some brighten faster approaching perihelion than they, dim receding. Some plateau, some spike in outbursts. 3I Atlas, with its unusual composition and possible cosmic ray-processed crust, may not follow standard patterns. The November observations established the post-perihelion baseline. Subsequent observations through December and January track the evolution. By late December, when the comet makes its closest approach to Earth at 1.80 astronomical units, 269 million kilometers, on December 19th, we will have 6 weeks of ground-based photometry. That data will constrain the activity curve. It will inform models of the nucleus composition. It will reveal whether the perihelion surge was explosive or sustained. The spectroscopic data matters too. Pre-perihelion, the James Webb Space Telescope observed 3I Atlas on August 6th with its near-infrared spectrograph. Results announced August 25th showed the comet unusually rich in carbon dioxide, with small amounts of water ice, water vapor, carbon monoxide, and carbonyl sulfide. This composition differs from the previous interstellar comet, 2I Borisov, which showed high carbon monoxide abundance. It differs from typical Oort cloud comets in the solar system, which tend toward water-dominated compositions at similar heliocentric distances. 3I Atlas appears to be a carbon dioxide-rich variant, possibly reflecting formation in a colder region of its origin disk or extended cosmic ray processing, converting carbon monoxide to carbon dioxide over billions of years. Spectroscopy in November will show if this composition persists. Ground-based spectrographs can measure emission lines from carbon molecules, cyanide, hydroxyl radicals, and other volatile fragments. If the blue color observed by LASCO near perihelion traces to dicarbon emission, November spectra should show strong dicarbon bands. If the color returns to red, indicating dust dominance, the spectra will show a continuum with weaker emission lines. The Nordic Optical Telescope, the Southern African Large Telescope, the Very Large Telescope, multiple facilities observed 3I Atlas pre-perihelion and obtained spectra. Those same facilities can observe post-perihelion. Comparing pre- and post-spectra directly tests whether perihelion changed the comet's outgassing pattern, whether new volatile species activated, whether the nucleus exposed fresh material. The photometric rotational period adds another constraint. Observations from July 2 to 29 by Santana Rose and colleagues established a spin period of 16.16 hours plus or minus 0.01 hours DAUS, with light curve amplitude approximately 0.3 magnitudes. This rotation rate stayed consistent over a month. If the nucleus lost significant mass at perihelion, if asymmetric outgassing produced torques, the rotation period might change. Monitoring the light curve through November and December will detect any spin-up or spin-down. It will also reveal if the light curve amplitude changes, which could indicate changes in nucleus shape or reflectivity distribution. The November observations contribute to this long-term photometric campaign. Every night of data adds points to the light curve. Fourier analysis of the combined dataset refines the period determination and detects any secular evolution. The tail morphology tells its own story. Hubble images from July showed a faint, broad anti-solar tail pointing eastward, away from the sun. Gemini South images from late August showed the tail grown to 30 arc seconds, 56,000 kilometers long. The broad appearance suggested high-speed ejection of small dust particles. Then the sunward jet observed in July and August by multiple teams, including Chandler and colleagues, a feature pointing toward the sun rather than away. Sunward jets indicate anisotropic mass loss from the day side of the nucleus, where solar heating concentrates. They are common in comets, but the 3I Atlas jet appeared unusually prominent. November observations will show if the jet persists post-perihelion. They will show if the anti-solar tail continues to grow, or if dust production declines, causing the tail to fade. Tail length and brightness correlate with dust production rate. If the tail remains visible and extended, dust continues to escape. If it shrinks, production is dropped. The particle size distribution in the coma also matters. Pre-perihelion observations suggested a deficit of submicron dust, with large particles dominating. This produces a homogeneous coma without a distinct tail, because large grains are less affected by radiation pressure and remain near the nucleus. Hubble reported dust mass loss rates of 6 to 60 kilograms per second in July. Those are large grains. If the perihelion encounter fragmented the nucleus or shattered surface ice, it might produce more small grains. Polarimetry can distinguish grain sizes. Pre-perihelion polarimetric observations by Santana Ross and team using 4S2 on the Very Large Telescope, Alfosk on the Nordic Optical Telescope, and 4RO2 showed extreme negative polarization. Minimum value minus 2.77% at phase angle 6.4 degrees Ossus. Inversion angle 17 degrees. This combination is unprecedented. It does not fit high polarization comets like Hale-Bopp, low polarization comets, or even F-type asteroids. November polarimetric follow-up will reveal if the polarization signature changes post-perihelion. If it does, the grain population has evolved. If it remains constant, the coma structure stayed stable through perihelion. All of this depends on the baseline. Zhang's October 31st and November 2nd images provide that baseline. Without them, we cannot calibrate post-perihelion against pre-perihelion. Without distributed amateur observations in early November, we cannot track daily evolution. Without the IAWN campaign starting November 27th, we cannot achieve the astrometric precision needed to detect subtle trajectory changes. The November 1 to 3 window is not just observation, it is the foundation for months of subsequent analysis. Every photon captured, every position measured, every spectrum recorded adds to the data set that will ultimately characterize this interstellar visitor. The stakes are scientific and practical. Scientifically, 3I Atlas represents only the third interstellar object confirmed. Each one teaches us about the population of bodies drifting between stars, about the ejection mechanisms that populate interstellar space, about the diversity of planetary system architectures across the galaxy. 1I Oumuamua was inactive, elongated, tumbling, with non-gravitational acceleration and no detected coma. 2I Borisov was a carbon monoxide-rich comet with dust properties broadly similar to solar system comets. 3I Atlas is carbon dioxide-dominated, nickel-bearing, with extreme polarization and possibly the oldest comet ever observed. 3 objects, 3 profiles. The sample is tiny, every measurement counts, every observation refines the statistics of interstellar bodies. Practically, 3I Atlas offers a test case for rapid response observational campaigns. When an interstellar object enters the inner solar system, we have limited time to study it. Discovery often occurs only months before perihelion. Telescope time must be allocated quickly. Coordination across facilities, space missions, and amateur networks requires planning. 3I Atlas benefits from advance notice, discovery in early July, perihelion in late October, over 3 months to mobilize. Future objects might not. The Vera C, Rubin Observatory. Coming online in 2025, TRUS will detect fainter objects at greater distances, providing longer lead times. But even so, interstellar objects move fast. Their hyperbolic trajectories bring them in and out of the inner solar system on timescales of months. Efficient observing strategies matter. The November observations of 3 I-Atlas demonstrate how distributed observer networks complement professional facilities. While large telescopes cannot point low on the horizon, smaller instruments can. While space telescopes have limited observing time, amateur networks provide continuous coverage. The synergy works. The data continues to accumulate. By November 10th, the comet will have risen significantly. By mid-November, major observatories resume tracking. Hubble plans ultraviolet spectroscopy in November to determine sulfur to oxygen ratios and gas emission composition. The telescope will monitor the comet as it recedes from the solar system over the following months. James Webb Space Telescope has its next observation scheduled for December after perihelion to compare post-perihelion composition with the August data. Together, Hubble and Webb provide complementary wavelengths, ultraviolet, visible, near-infrared, covering the full spectrum of cometary emissions. Ground-based radio telescopes add another dimension. The James Clerk Maxwell Telescope observed 3 I-Atlas on September 7th and found hydrogen cyanide production rate 1.5 times 10 to the 25th molecules per second. 1 week later, production had climbed to 4.5 times 10 to the 25th molecules per second, approximately 2 kilograms per second. Radio observations in November will show if hydrogen cyanide production continues post-perihelion or drops off. This constrains the volatile inventory and the temperature distribution within the nucleus. The multi-wavelength campaign paints a complete picture. Optical images track dust and overall brightness. Spectra identify molecules. Polarimetry characterizes grain sizes. Radio observations measure production rates. Astrometry refines the orbit. Each technique contributes unique information. Combining them yields models of the nucleus composition, size, shape, rotation, activity mechanisms, and evolutionary state. The November ground observations, beginning with Zhang's October 31st baseline image, anchor the optical component. They provide the time-resolved record of how the comet looked immediately after perihelion, day by day, as it climbed from the solar glare back into observable sky. The physics demands this precision. Comet activity depends on solar heating. Ice sublimates when surface temperature exceeds the sublimation point for each volatile. Water ice sublimates above about 200 degrees Kelvin. Carbon dioxide sublimates above 150 degrees Kelvin. Carbon monoxide sublimates at even lower temperatures as 3. I-Atlas approached perihelion, its surface temperature rose. Carbon dioxide began sublimating first, cooling the surface and suppressing water sublimation. This is the hypothesis from Zhang and Badams. At perihelion, water suddenly activated, producing the rapid brightening and blue gas emission. Post-perihelion, as the comet recedes and surface temperature drops, water sublimation should decline first. Carbon dioxide, with lower sublimation temperature, may persist longer. The November observations test this. If the comet dims in step with decreasing solar heating, standard volatile sublimation explains the activity. If anomalies appear, unexpected brightening, sustained high activity, color changes, alternative mechanisms activate. Subsurface ice exposure. Stored heat release, structural changes in the nucleus, fragmentation. The fragmentation scenario matters. Some comets split at perihelion. Thermal stress cracks the nucleus. Outgassing pressure fractures weak zones. Comet Shoemaker levy. 9 famously fragmented when it passed too close to Jupiter, tidal forces tearing it apart. 3 I-Atlas at 1.36 astronomical units from the Sun experienced less stress, but not zero. If the nucleus was already weakened by cosmic ray processing, by thermal cycling over billions of years in interstellar space, perihelion might trigger splitting. Zhang's November images show no obvious fragmentation. The nucleus appears as a single condensed source, but subtle fragmentation, small pieces separating slowly, might not be immediately visible. Follow-up observations over weeks will reveal if the coma morphology changes, if multiple condensations appear, if the light curve shows irregularities. Fragmentation events sometimes produce brightness. Outbursts days or weeks after perihelion as fresh ice surfaces suddenly exposed begin sublimating. Monitoring continues. The countdown to December 19th accelerates. The closest approach to Earth, 269 million kilometers. Not close by terrestrial standards, almost twice the Earth-Sun distance, but the closest this interstellar traveler comes to us. The geometry shifts. Earth moves toward the comet as the comet recedes from the Sun. For a brief period, both motions partially cancel, slowing the apparent recession. This extends the observing window. Through late December and into January, the comet remains accessible to moderate-sized telescopes. By Christmas, it passes near Regulus. By late January, it crosses into sextans and begins fading below magnitude 13. The Vera Rubin Observatory, with its large aperture and wide field, will continue tracking it longer, but for most observers, the best months are November and December. The November 1 to 3 baseline images mark the opening of this window. The final trajectory takes 3I Atlas back into the outer solar system. It passes 0.36 astronomical units from Jupiter on March 16, 2026, 54 million kilometers. NASA's Juno spacecraft orbits Jupiter. Juno might glimpse the comet. Calculations suggest if Juno had its initial fuel reserves, it could intercept, but it does not. No spacecraft will visit 3I Atlas. No lander will sample its surface. No probe will analyze its composition in situ. All we have are remote observations. Photons captured across wavelengths, positions measured against the stars, spectra revealing chemistry. This is the limitation and the challenge. We must extract maximum information from photons alone. Historically, this is how we have studied most celestial objects. The sun, the planets before spacecraft, the stars, galaxies, quasars, remote sensing. 3. I-Atlas continues this tradition, but with higher stakes. It carries information from another stellar system. It tells us how worlds form elsewhere. It hints at the diversity of planetary architectures. If our solar system is typical, interstellar comets should share our composition. They do not. 1I Oumuamua showed no cometary activity. 2I Borisov was carbon monoxide rich. 3I Atlas is carbon dioxide rich with extreme polarization. 3 samples, 3 outliers. This suggests planetary systems vary widely in composition, volatile content, and formation conditions. If we want to understand exoplanets, their atmospheres, their potential for life, we need to understand the building blocks. Comets are those building blocks. Interstellar comets sample a wider population than solar system comets. The November observations of 3I Atlas contribute to that understanding. The question that shadows all observations: what if the anomalies do not resolve? Loeb's list of 9 properties includes the low inclination retrograde orbit, the sunward jet, the enormous mass compared to previous interstellar objects, the fine-tuned timing to be unobservable from Earth at perihelion while passing close to Mars, Venus, and Jupiter, the unusually old cosmic ray exposure Hg, the enriched nickel to iron ratio, the extreme negative polarization, the rapid brightening and blue color near perihelion, and the potential non-gravitational acceleration without visible debris cloud. Each individually has low probability. Together, the cumulative likelihood drops to parts in 10 quadrillion according to Loeb's calculations. He assigns the Loeb scale rank of 4 out of 10, or in the zone where natural explanations strain but remain plausible, and technological origins cannot be excluded. The November observations cannot answer this conclusively. They can, however, rule out certain scenarios. If the comet fragments, natural processes dominate. If the coma expands as expected, standard physics applies. If the orbit follows gravitational prediction with no anomalous acceleration, technology is unnecessary. Conversely, if the comet shows unexpected maneuvers, if the activity defies thermal models, if structures or signals emerge, the anomaly count rises. The baseline from Zhang's October 31st and November 2nd images allows comparison. Every subsequent observation either supports natural interpretation or adds to the anomaly list. By December, when Hubble and Webb add their data, when JUICE results arrive in February 2026, the case will clarify. Science is self-correcting. Hypotheses face data, models adjust. The initial speculation that 3I Atlas might be artificially large faded when Hubble resolved the nucleus to less than 5.6 kilometers. The extreme brightening near perihelion now has a proposed mechanism: carbon dioxide, suppressed water sublimation, followed by explosive release. The blue color traces to gas emission dyes, which is unusual but physically plausible. The nickel vapor detection has a potential explanation. Nickel tetracarbonyl, a volatile compound that photodissociates under ultraviolet light. Each observation either confirms natural comet behavior or demands further explanation. The process continues. The November ground observations are one step in this process. The scientific method requires transparency. Zhang's images are public. The Arxiv preprint is open access. The Lowell Observatory confirms the observations. Amateur astronomers replicate them independently. The data is not hidden. The analysis is not secret. Anyone with a telescope and clear skies can participate. Anyone with computational skills can analyze the photometry. The raw data flows into the minor planet center. the astrometry feeds, orbital models. The community scrutinizes. This is how we distinguish signal from noise, anomaly from artifact, discovery from error. 3, iAtlas will fade from view over the coming year. By mid-2026, it will be beyond reach of all but the largest telescopes. By 2027, it will cross back out through the orbit of Jupiter. Headed for interstellar space, it will drift for billions more years, perhaps encountering another star system, perhaps not. Its brief passage through our solar system, 6 months from discovery to perihelion, another 6 months receding, offered a window. We observed, we measured, we recorded the November 1 to 3 ground observations, beginning with Zhang's October 31st baseline, captured the critical post-perihelion state. They documented what happened after the closest solar approach. They established the foundation for months of follow-up. This is the work, not speculation, not hype. Observations, measurements, data. Zhang sat at the telescope controls Halloween morning and pointed at coordinates. He captured photons that traveled over 100 million kilometers from a body that formed billions of years ago in another star system. He processed the data. He shared it. The astronomical community responded. Amateur networks mobilized. Spectroscopic campaigns launched. The International Asteroid Warning Network scheduled astrometric monitoring. Hubble and Webb planned follow-up. The machinery of science engaged. Not because of conspiracy theories or alien mothership fantasies, because an interstellar object passed through our solar system and we had a chance to learn from it. That chance depended on people like Zhang doing the work, capturing the images, publishing the findings. The November observations matter because they are real, documented, verifiable. They are part of the permanent record. When future astronomers look back at the passage of 3i Atlas through the inner solar system in 2025, they will see Zhang's October 31st image. They will see the November 2 amateur detections. They will see the data from IAWN's campaign. They will know what we observed, how we observed it, and what we learned. The comet continues its journey. The data continues accumulating. The analysis continues refining. By December close approach, we will have 6 weeks of post-perihelion photometry. By February, JUICE results will arrive. By mid-2026, Hubble and Webb will have completed their monitoring campaigns. The full data set will span a year. From discovery in July through the final observations in 2026, that data set will characterize 3. iAtlas more completely than any previous interstellar object. It will constrain models of interstellar comet compositions. It will inform predictions for future interstellar visitors detected by Vera Rubin Observatory and other next-generation surveys. It will add to our understanding of how planetary systems form and evolve across the galaxy. And it all traces back to specific observations at specific times by specific people. Zhang at Lowell on October 31st, amateur astronomers across the northern hemisphere in early November, the distributed network capturing the critical window. The final line is not a moral. It is a fact. On October 31st, 2025, Cheeching Zhang captured the first confirmed ground-based optical image of interstellar comet 3i Atlas after perihelion. The nucleus remained intact. The coma showed no fragmentation. The smudge on the detector represented photons from another star system. That image, and the amateur observations that followed on November 1 through 3, established the baseline for understanding what happened when the comet passed closest to the Sun. In 50 years, when 3i Atlas is beyond Pluto's orbit, drifting back toward interstellar space, the November data will remain archived, documented, the permanent record of the moment we glimpsed an ancient traveler and measured its passage through our small corner of the galaxy.